ब्लूटूथ का है, उसकी नहीं जरूरत, बैग में है वैसे तो, चेक कर ले साउंड वगैरह है ना। जूम इस पे भी, जूम इस पे चल रहा है। ज्वाइन कर। जूम से भी ज्वाइन कर लो, थोड़ा सा नहीं पार्टिसिपेंट्स हैं, प्लीज़ ज्वाइन
फिर अगर मैंने कुछ बोला तो फिर
सबको बोलो जूम पे ज्वाइन करो, मैसेज करो, ग्रुप में डालो मैसेज, है ना, ठीक है। बैटरी देना है।
Good morning, sir.
Good morning, Dr. Arun. How are you?
No, sir, this is Narendra, sir.
Hi, Nandar. Where are you? Sorry. Hi,
Uh, I'm good, sir. How are you, sir?
are you enjoying your stay in India
Yes, sir.
with the conference, with the workshop? Very good, very good.
Yes, sir. With the concept. How's everything there, sir?
You know, I was busy preparing the lecture in the last 2 days. It
Yes,
coincided
sir.
with the that I have to submit some research proposals due with due dates and
Yes.
paper with revision with due dates. So I was squeezed. So I didn't follow the program of the workshop. So I missed that one. But anyway, I'm
Yes.
reading the lecture, but I feel pity that I didn't follow the workshop. But maybe after today, I will have the opportunity.
So we had only two or three lecture online, and other are just hands-on sessions offline.
So are you sending the links every day, or what do you do?
For what, sir?
For the lectures every day?
For 2 days?
You know, is the links changing every day, so you update us, or what do you do?
कौन सी सर का लेक्चर हो रहा है ये?
Yeah.
Yes, sir. I will share, sir.
Okay.
Yes, sir.
I say hello to Professor Fang and Professor Vijay Kumar. They are linked also here. These are my colleagues.
Yes, sir.
Okay, Dr. Arun, we are ready anytime you like.
Dr. Good morning.
Good morning. Hello, Dr. Arun.
Yeah, so I welcome you. So I'm just starting. Let me briefly introduce you first of all. So it's my I thank you from the core of my heart that you are with us for this workshop, and I also welcome Professor Vada Al-Flazi, Vijay Kumar, Mr. Narendra, and all the participants. Let me briefly talk about your education. So you have done your PhD in physics from University of Minnesota, USA in December 1991, and MSc in physics, University of Minnesota, USA, and BSc in physics, Oran University, Algeria. Then regarding your employment, Professor Tit is the postdoctoral fellow at ICTP, Trieste, Italy, and assistant professor of physics, Department of Physics, UAEU, Al-In. Now he is a full professor at Al-In, Abu Dhabi, and he is awarded with the various awards. So in 1997, he was awarded with the Abdel Hamid Shauman Prize in Physics, Amman, Jordan, and Khalifa Award for the University Professor Distinguished in Research. It was awarded to him in the 15th April 2013. Then another awards awarded to him in 2002 and 2003, April 2009. Various type of awards have been awarded to Professor, and he visited so many places as a scholar of physics. So in summer visits, he went to the Abdus Salam ICTP Trieste, Italy in 1994, 1998 and 2004. Physics department, Vanderbilt University, USA in 1995. Then he visited Iowa State University, Ames, USA 1996, and Ottawa, a collaboration for 6 years, 1997 to 2002. Physics department, University of Minnesota, Minneapolis in 2003, he visited there. Then he visited so many other places in 2009, 2010, 11, 13, 16, and he also visited India, JNCSR, Bangalore, India in the summer 2012. It's a prestigious institute of India, JNCSR. And he also visited in May 2022 Singapore, NUS Physics Department. And he published about 120 research papers in various journals. So now I request Professor Nasir please give his talk on the topic relevance of defective and functionalized TMDs, MX2, MO, M means MO and W, and X is SSENT tellurium, monolayers for photonics, spintronics, energy storage and gas sensing applications. It's basically a DFT study. So it will tell you that how DFT help us to design various materials which are helpful in photonics, spintronics, energy storage devices and gas sensing applications. So please, sir.
Thank you, Dr. Kumar. So can you give me the chance to be co-moderator or something?
This meeting is being recorded.
So can you, Dr. Kumar, and the participants see the screen?
Yeah, screen is visible.
Visible, yes?
Yeah.
Very good.
Please
So I welcome everyone to this lecture. And please mute your microphones. I will start now describing the lecture. So as said, thank you, Dr. Kumar, for a long introduction. The title is Relevance of Defective and Functionalized Transition Metal Decyclogenide, MX2, where M stands for molybdenum and tungsten, whereas X stands for cyclogenide, sulfur, selenium, tellurium. Monolayer for photonic, spintronic, energy storage, and gas sensing applications. It's a diversity of work that was done by my PhD students, and especially Watha in this lecture, because I have also maybe 10 days ago, one student graduated from my group with PhD, her name Saba Khan. She did some different systems. She studied C2N and mixing for diversity of applications. So it was also very nice work that she did. She published about 6 papers, top journals papers, plus 1 proceedings. Whereas Watha, she is doing even more productive. She published now 6 papers in journal papers, and 1 conference proceedings to present in this month in Sharjah. And she has both potential to publish maybe 4 more papers. Anyway, so basically what I'm presenting is the results of other people, of my students, especially Watha, contributing to this talk maybe about 80%. And the other 20% is due to the collaboration with the Indian group of Arun Kumar and his students and his professors there, Singh and Elwalia and other his PhD students, Anjana Devi and others. So I will acknowledge them when I describe the paper. Anyway, so to introduce to you that where are we located? We are located in United Arab Emirates, and the United Arab Emirates University is located in a city, small city, called Al Ain. Al Ain, maybe you can see it on the map there on the top right. Al Ain, small city, it's far away from Dubai by 120. If you go north, you hit Dubai. If you go west, you hit Abu Dhabi, the capital, at a distance of 150 kilometers. So the Al Ain city, as I wrote also about some information to just publicize the place that we have here. United Arab Emirates consisting of 7 emirates, population about 10 million. Abu Dhabi is the capital, 1.5 billion population. The Dubai is the biggest city, close to 4 million actually. Maybe the capital, economical capital of the country. Sharjah, it's the same as big as the Abu Dhabi. And you have Ras Al Khaimah, Fujairah, Ajman, and Qaywin. These are 7 emirates. So the area is a small area, about 83,000 kilometers square, and it's located toward the east of the Arabian Peninsula. And Al Ain University is located in Al Ain, as I said. We have other universities. Actually, when I came here about 30 years ago, we had about 13,000 students, but now we have about the same, about 15,000 students. Why? Because many universities appear in the country. So the growth in population is taken by other universities like Khalifa University in Abu Dhabi, New York University Abu Dhabi, Sharjah University in Sharjah, and American universities here and there in Dubai, in Sharjah, in Ras Al Khaimah. So many other universities that you named them. Basically the university has about 15,000 students basically. The ranking, they say it's about 287, which is among good ranking. Because they are supporting research, especially in the recent years, since 2015. So the strategy has been changed drastically, like first order phase transition. So research, every faculty basically can have up to 2 research grants, and we start having PhD programs. Our master program started in material science and engineering. It was started in the year 2000 or 1999. After they start putting masters in the different disciplines and PhDs. PhDs started in 2015, and we have also supercomputer. We start having a kind of first based on vision. So we start having postdocs and PhD students. So we start doing real research, and we start publishing in top journals. Especially, we have now packages like VASP, like ATK, like VN2K, like many others. So we are doing good. So do you hear me, Arun?
Yeah. Yes, sir. We hear you.
Okay, then I keep going.
Yeah.
So the outline of the talk is that I will describe in the beginning some background and motivation, because it's workshop, it's not conference. So I will go to introduce some topics, but I try to be very fast there, because I have too many papers to present, at least 4 papers, which is not what I wanted. I wanted to present about 7 papers, but it seems it's impossible to within given 1 hour that I have, which is long time for the talk, but to cover too many papers, there is optimum to go, Anyway, so the second computational methods, it's based on VASP and ATK. Vienna AB initial simulation package and atomistic toolkits, and I will describe the results. I don't think that I finish all of them. So I start with photonics, where I deal with the alloys, common anion and common cation alloys of transition method Deshak-Ozonide monolayer, because monolayers it has direct band gap, so it suits the photonic application. So we will deal with monolayers, and nowadays, to the systems are leading materials. So, which is to our advantage in computation, because we want system to be small, to have better accurate calculations, and because we are limited with the size. So number 2, spintronics. I will describe that maybe it's misleading. It's hard metallicity basically, and we use it in hard metallicity either in spintronics or gas sensing. But in my case, we are using the application hard metallicity in more gas sensing. Anyway, we show that we obtained the hard metallicity in defected as well as transition metal doped TMD, transition metal Deshak-Gonzalez. Then number 3, hydrogen storage, where we have a combination of bilayer, graphene transition metal doped transition metal Deshak-Gonzalez monolayer. So these B layers are going to have high uptake capacity in hydrogen storage. So I don't think I will have enough time to go to biosensors, where I show the detection of VOC, lung cancer biomarkers, which is very fascinating, and we have paper which is ready for submission. All of this with what? She is very outstanding. And also she supplied me recently also bought another paper on batteries and another paper on gas sensing. So you can see she worked on photonics, spintronics, hydrogen storage, biomarkers, batteries, gas sensing, all these in her PhD. Whatever I mentioned to her as ideas, she start cooking the meal. So she is very formidable. Anyway, so I will conclude the talk. So in the background and motivation, as you know, the story of 2D material started by the exfoliation of the graphene by Game and Novoselov. So in graphene, as you can see, it's a structure which is hexagonal honeycomb structure of carbon, and if it's multi-layers, we call it graphite. If you for the graphite carbon tubes or Becky balls. Anyway, it's known that it is metallic because there is closure of the band gap at IK corner of the B1 zone. So the people who got Nobel Prize, Game and Novoselov, they were successful to using the Scotch tape exfoliation of graphite. They separated the 1 molar thickness of graphene, and they did also the what do you call it, angular resolved photo emission spectroscopy, where they show like conic or there are cones in the valence band. So they showed it in their experiments. So they deserved Nobel Prize, and the guys are very active actually. One of them, Game, is still in Manchester, and Novoselov is in NUS, National University of Singapore. So they are still active, publishing, of course, Nature Communication, Nature Material, Nature Physics. So it's very amazing. They are both experimentalists, and I recall one paper where they showed the relevance of 2D system or graphene for detection of individual gas molecules with high sensitivity. That's their expectation. They have huge faith in the graphene and in 2D systems. They are moving. They do different 2D systems, and they include in their groups, of course, simulations. Anyway, so let me move. So the synthesis now for the MOS2, it comes thereafter. The Nobel Prize was offered to these two people on 2010. 2011, many materials appeared, starting from transition metal dehydrogenase to mixines. Mixines also the same year. 2011, mixines appeared by Yuri Gogotsi. So the many materials appeared in the applications of 2D systems. So the bulk of MOS2, which is the first one, it's very popular transition metal dehydrogenase. This is the original one. Is diamagnetic, and it has under band gap semiconductor when it is in the bulk structure, similar to silicon. With energy gap, it's 1.23, whereas silicon 1.14 or something. It is composed of stacked monolayers held by van der Waals interactions. In nature, it exists in 3 phases. It exists in 2H, the hexagonal MOS2 hexagonal. These structures are on the right side. And it has second structure, which is 3. We call it 3R, 3 rhombohedral, and one more structure, which is tetragonal structure. The first 2 structures are under what do you call it, like prismatic trigonal prismatic symmetry, whereas the tetragonal, it has octahedral symmetry. The metals have octahedral symmetry. Anyway, the method to grow the monolayer, because we are carrying both monolayer, is either from, like we said, the top-down technique, like exfoliation, or it can go also from bottom-up technique. But here, if there are 2 methods that I mentioned here, PDMS, which is a chemical method, and liquid phase exfoliation can be used to produce monolayers of MOS2 with energy gap. It's much higher than the bulk the bulk is at 1.23. The monolayer has a direct band gap and higher, which is more suitable for photonic application, because this one is close to the green color. So the person who fabricated the in 2011 the MOS2 monolayer is the reference is there. The what do you call it? The structure, the band structure of the. Well, let's start from the atomic. Atomic, you have either here I showed only the picture of the one monolayer, but in the monolayer, you have here the yellow color is sulfur, the purple is molybdenum. So the molybdenum is under symmetry, which is trigonal prismatic. So it's where it has about six neighbors, six sarcosonides around it, and the sarcosonide it's under what we call like pyramidal symmetry, the covalent bonds with the metals. So the lattice constants are mentioned there. A and B is 3.16, the bond length is 2.41, and the thickness of the monolayer is 3.17. The angle between the sulfur, molybdenum, and sulfur is 82, and the bulk structures are the electronic structure is also shown there. But I am marrying here the band gap of experimental value. The bulk is 1.23, so the experimental value, but the theoretical band structure looks like this. It's indirect band gap, whereas the monolayer has direct band gap at K corner with the value of 1.86 experimentally. Okay, then I move on. Special characteristics about the valence band maximum and conduction band minimum is that very important, because this kind of material, the band edges are predominated by the metallic states. It's not like semiconductors. Like compound semiconductors 3.5 or 2.6, the valence band is known to be anions, anion originated from anions, and the conduction band from cations. So here it's purely from metals, both of them. So that's why is so? Because I will show some what you call it group theoretical splitting of these states under different symmetries. Here under the octahedral symmetry, OH, like in the case of oxides, or T1 that I mentioned, tetragonal of the third phase that I mentioned for the transition with the sarcosonide. It has octahedral symmetry. So octahedral symmetry, it means the metal is surrounded by 6 oxygen, or like TiO2, for example. So it is in rotile structure. The TiO2, the titanium, is under octahedral symmetry. It is my material that I studied in PhD. So I didn't forget to maybe bring the structure of TiO2, but it's irrelevant for this talk. So these states split into 2 groups, EG and T2G. T2G contains 3 states, X, Y, Y, Z, ZX, and EG contains 2 states, which is Z square, X, Y square, minus Y square. Whereas in the trigonal prismatic symmetry of our case, which is transition with the sarcosonide, so the metal is surrounded by 6 sarcosonide atoms. So that symmetry breaks these states, split it into three groups. But amazing that the one group, which is A1, which is singlet, and you have singlet and doublet. So the singlet is very far, but it makes a gap about 1.3 electron volt or something like that, and it will consist the conduction band, the valence band edge. So the second group, E2, E prime, it consists the conduction band edge. So it's in contrast to the oxides, or the splitting of these states occurs in the conduction band. So this consists the conduction band in the oxides, whereas in transition with the sarcosonide, you have the valence band edge is consisting of metallic state originating metallic, Z square. And the conduction band edge is consisting also of metallic of 2 orbitals, XY, X square minus Y square, the orbitals. Anyway, but that's in the monolayer. Similarly for the Berg, it's same splitting, but we have, due to the van der Waals interaction, there is of tailing into the band gap of some states, and there is mixing between for the Berg. In the Berg, not purely
Recording in progress.
So Arun, do you still hear me?
Pardon, sir?
Arun,
Pardon, sir?
do you still hear me? Yeah.
Yeah, hear you.
Yes, sir, you are audible, sir.
Okay, very good. So I keep going. So I said all this I have described. I think what I wrote in the remark, but I mentioned them in my description. So now, comparison between transitional method decyclozonide and mixine monolayers. So in the transitional method decyclozonide, you have as said one metallic layer, and it is sandwiched between two cyclozonide monolayers. If you look from side view, you find like this. So you have the atomic monolayer, and it's surrounded top and bottom by the cyclozonide monolayers. Whereas in the mixine, you have the number of monolayers of metallic are more than the cyclozonide. So, or maybe not cyclozonide, it has another layers which are either carbon or nitrogen. So and the too many mixines have been grown, and with different thicknesses. The thinnest one may be Ti2C, and plus the passivation layer can be oxygen or other passivation layers. So the most popular one, maybe the original one that was grown by Gogotsi, is Ti3C2O2, or maybe other, he has some different passivation. Usually for fullerene elements are also there. So you can see here that they have this different perspective of monolayer. So it is thicker than the transition method decyclozonide, and it is the topest layers are metallic. So like here, the carbon is in black in the right hand side, and the yellow colors are the metal or titanium. So you have the more layers of titanium, and the topest ones are the metallic. So the metallic layers are usually passivated by passivation, that we call functionalization of the material. They can be functionalized by oxygen, sulfur, sorry, I didn't correct my CS was small letter because according to the periodic table, or OH group, or fullerene with OH. Anyway, so all these are passivations, possible passivations for the transition method for the mixines. So we did also we did use them in our work. So Saba did use the mixine, and the publication is under review for their application in batteries. Also, what I did use also mixine for VOC or for lung cancer detection, and also for batteries. So we are using also mixines. But my talk today focuses on transition method decyclozonide. So I want to show some superiority there more than mixine. But of course, mixine is competing to be leading. So don't underestimate mixine. Anyway, so now computational method. Computational method, we use VASP and we use ATK. Probably this part I should maybe go very fast. It's very, you can learn about it. VASP, I have described here very detailed. But we use the density functional theory with two of Constraint equations in K-space, Riemann zone, to explore the crystalline translational symmetry. So it will cost us less to go to the Riemann zone. This goes beyond, sorry, I have this one bothering me. So it goes beyond bond open hydro approximation, of course. So we deal with only electrons, not ions. In DFT, the electronic density is taken as the main parameter in rho v iterations to converge to the ground state density, and thus to obtain total energy. See DFT cycle next view graph. Atomic relaxation should be carried out in outer loop in looking for the optimal atomic configurations. And I believe most of the attendees they have that experience. It is customary to include vendor-well interactions using green scheme in case of existing transition metal structures. In case of transition metal atoms in the system, we have to use spin polarization, and U-Hubbard should be considered. Sampling of the B1 zone is usually done using Monkhorst pack techniques. Conversion criteria are usually taken about 10 to minus 6 electron volt for the energy and 1 milli-electron volt per angstrom for the force. As outputs, we use total energy to calculate the binding energy in case of metals embedded, or absorption in case of molecules on the surface of the system, or recursive energy in case of, for example, hydrogen storage to look for the uptake capacity, or batteries also to look for uptake capacity of metals. We calculate also magnetization, change of or transferred charge using Butler charge analysis. On the other hand, the atomistic toolkit is very relevant for transport calculation. So they complement each other. So therefore the electronic structures is best to use the VASP. It's the very popular package. So definitely without any probably competition. And whereas atomic toolkit is maybe the only one which is for transport, relevant for transport. It calculates transport based on a combination of DFT and non-equilibrium Green's functions. And it deals with the two-terminal Landauer Büttiker formula, and it's shown there. From the IV curve, one calculate the differential resistance, and thereafter the sensor response. Okay, we have some works published about that, maybe applied surface science in my group, and of course there you can find more references which are more original. So now, regarding DFT, as I said, we start with initial guess of density, charge density, and we start iterating. How do we calculate the effective potential, which we call Constran the potential, which is the external potential, which is like pseudo potential, which is the interaction of the electron with the ions, plus the Hartree term, which is the interaction of the electron with a single electron interacting with the remaining electrons like density. So there is Hartree term there, which is very possible to converge, and plus the exchange correlation potential. So we make the Schrodinger equation. So and we solve this Schrodinger equation in case as I mentioned before. The calculation of density. After that, after we get the eigen functions, we calculate the density, and from density we calculate the potential, and we test before we start iterating, of course, whether the density or maybe the main parameter is like nowadays H&S. So similarly, we test the total energy. If the total energy converges, we finish. Otherwise, we iterate, and that's called density iteration. Beyond this, there is another bigger loop where we change the configuration, atomic configuration, but we displace the atoms based on the forces calculated on each atom, and we look for the optimal or the stable configuration. Anyway, so the first application that I'm going to describe, I'm running this behind my time. So the first application is photonic, where we study here the band gap bonding effect in transition metal disaggregationite alloys, ternary alloys. So we use this paper is already published 2021 in New Journal of Physics. We use transition metal disaggregationite diversity, maybe I think about 3 of them. And we use supercell, which is very small, 2x2 primitive cell, which consists of 4 cations and 8 anions, 12 atoms. And we use for that CS tab because we were lucky, me and Watha, that ATK was giving band gap, which is very close to the experimental band gaps. So here you can see here and this table that I'm comparing the MOSE2, MOSE2, and the tungsten S2. So the theory and the experiment. You can see here that because some research are very close in case of monolayers, because monolayer I said that it is the band gap. So now on, I don't mention monolayer. I don't mention it's also so add here for photonics because they have the band gap. Fitting to experimental or comparing to experimental data, we are not off. We are less than 10% away from the experimental values. So we trusted that we have the band gap which is close. So we started doing alloys. So the alloys that we have some experimental data that we were modeling. We were happy to collect many data. So for example, here I mentioned the alloy MOS2, 1 minus X SE2X, and another alloy which is MO 1 minus X and WX S2. She says, like we have here in the first alloy, we have common cation because MO is common, and in the second case, like we have common anion. So I wanted to compare whether the rule of the whether the rule is similar to the compound semiconductors or different. Of course, it's completely different. That's the experimental what do you call it? What it shows in experimental, because the bonding exists here in the case of common anion, whereas in semiconductor the bonding exists in common cation, and the linear variation exists here in common cation. Whereas in semiconductor common anion, so we want to show this, to publish this, and to show what is the origin of the bonding character. So here in this below the second row, it shows the theoretical data, and of course we have problem of configuration in the alloys. So we did all the configurations, and we were lucky that we found some experimental support. But the lowest energy gap is due to a uniform, or maybe what you call a uniform alloy, or what you call it homogeneous alloy. So which makes our case justify that we take supercell which is small. If 2x2 will be enough, and we convince the referees, because they raise this question: why did you use such small supercell? So unfortunately, we found an experimental paper showing that the minimum is due to the lowest energy gap is due to the homogeneous alloy. Okay. Anyway, but here you can see that we are linear fitting. We did linear fitting in the case of common cation, and we did parabolic fitting. But of course, we started with parabolic, which still looks like more linear. But I meant to be linear to compare to the experimental. So we found the law of Boeing is written in red. I remind my students that the energy gap should vary to energy gap of material A, compound A, times 1 minus X, plus energy gap of material B times X, minus B times X times 1 minus X. So you can see here minus times minus, it will be plus. So this B will be Bx squared. Bx squared means convex parabola. Convex parabola, the B is called Boeing parameter. So to the people, maybe to remember them, or to the people who didn't know this, that the parameter is defined by the coefficient of x squared. So the coefficient of x squared here, in our theoretical is 0.32 in case of this parabola, and in the experimental 0.26. So we have fitting, we have good fitting, good close laws. Similarly for the linearity, it's minus 0.33 and minus 0.33, which means we are doing good in the terms of fitting our data and comparing them to the behavior of experimental alloys. Now to investigate what is the cause of the Boeing, we did further investigation. So basically, we started with the homo-LUMO eigenstates. So on the left side, it shows for the common cation alloy, and we show here that starting from x equal to 0 to x equal to 1. And by the way, the minimum here is, of the parabola is about 0.25. Whereas here it's linear, so it does not matter. So we take x equal to 0, x equal to 1, and we hit x equal to 0.5. Whereas here, in the case of common anion, we use x equal to 0.25 because we meant to hit the minimum. Okay, so we did that. We did even the calculation of the wave function. So we did in case of linear or common cation, we did x equal to 0.5, So, and we show here, starting from of course, the lower one is the side view, and the upper one is the top view. So it has supercell, which is, well, it's a 2 by 2, and 2 by 2 primitive cells. So in case of the x equal to 0, you can see that the HOMO is consisting of z squared, and which we predicted by the group theory. Okay, so we use the group theory to split the D states into irreducible representations, and also we showed in that paper that it is z squared. That's the valence band edge. So and the HOMO, it seems it's z squared all the way. For all the way, it's always z squared, as you can see, because the direction which is horizontal is equivalent to z direction, which is the normal direction to the surface. In the left panel, okay. If we keep doing that for the right hand side, the case of common anion, you can see here also the same thing. So the valence band edge has z squared, okay, in all the way. But the conduction band, there is a little bit more caution to take. So in the conduction band, it's not z squared, it is x squared plus y squared and xy. So it is really planar. You can see the wave function is really planar. It's along the plane, which is x squared, y squared, x squared plus y squared, and xy. But you can and it is linear contribution by both what you call them, both metals. Only one metal here. We have only one metal, so basically contribution from molybdenum. But in this case, in the second case, where you have two metals, tungsten and molybdenum. So you can see here there are contributions from two atoms. No, the mainly molybdenum, and if you see top there, so you have molybdenum in blue color, and you have the or maybe like kind of turning to green, between green and blue. Whereas the dark blue is the tungsten. But in the tungsten, when you have x equal 0.25, is depleted, does not have contribution to the conduction band edge wave function. So it means there is competition between the tungsten and the molybdenum. So the molybdenum has taken that state. It means it has lower energy kind of. So in the conduction band. So there is competition between these two metals. So similarly, like we described before, the bonding inside the compound semiconductors. Similarly here, whenever there is two metals, there will be competition. And that competition will trigger the bonding. That's at least first thing to think, first idea to think. And we pursued here, for example, and the last view graph before I move to the next paper. So the last view graph here for the we compared me and Burke versus the monolayer, just to show that the tailing state in the monolayer are purely metallic. So and so here in the case of Burke, we have shown here the both bands and density of states, which is partial PDOS, partial density of states, due to contribution of atoms. Here molybdenum and sulfur, we are taking MOS2 in both cases, but Burke and versus monolayer. So in the case of Burke, you have some contribution from both species, where the molybdenum and sulfur. Whereas in the case of monolayer, mainly the tail is metallic. Mainly it's metallic. So maybe it's not very clear, but that's what also we want to convey. The edge states are metallic and are under control, are controlling the band gap. So the conclusion is that here bonding character in common anion transition with the functionalized monolayer alloys is attributed to the competition between cations, metals, in populating the conduction band monolayer. So in common anion there will be competition. If there is no common anion, it's a common cation. In that case, you have only one metal, so there will be no competition. So basically, the variation will become linear. Anyway, but one should learn also that the alloying the metal would give a broader range of tuning the energy gap, which means band gap engineering. Because you can see here, maybe for students also, sorry to maybe I want to be clear. So it's different when you vary the band gap from a certain value A to certain value B, whereas it varies from A to B and beyond it, there is tail due to the Boeing. So it means you have chance to absorb more light if you are applying it for like solar cell or something like that. But there is a Boeing. It means you have more broader range of energy gaps in your in gap engineering. So anyway, so I finished with the first paper. I moved to second paper. Second paper, it's about spintronics, but it's very, very long, this one, because it's two papers. Spintronics, but mainly I said it's application of half metallicity. And half metallicity can be an important pillar in spintronics, as well as in gas sensing. So we are exploring the metallicity in gas sensing. That's a new idea that we put forward in the community, that we explore the half metallicity for gas sensing. So when there is a landing of a molecule, the half metallicity get destroyed. So therefore there will be a big change in IV curve. So there will be, we can maybe look for selectivity issues. So anyway, so mainly we contributed in this gas sensing by different ideas. Among them is the half metallicity. One before also that we contributed before, that negative differential resistance. It can also have to be a huge contribution. And negative differential resistance can also be caused by varitronics or other issues. So but here we are focusing on half metallicity only, and we try to project it on the application of gas sensing. And it's very long. I don't know whether I can finish all this, but maybe it will be very brief. Here the contribution of two papers. One paper is due to defect, which induce magnetism, as well as half metallicity in MOX2. X can stand for sulfur or selenium, transition metal destructive monolayers. This is due to the work of the Indian group Anjana Devi, Neha Diman, Narendra Kumar, Watha Al-Falasi, Arun Kumar, Ahlawalia, I'm sorry, PK Ahlawalia, Amarjit Singh, and myself. Anyway, this is under review in Nanomaterials journal. They give the referees gave us a lot of its major revision. Anyway, so here they use supercell of size 4x4 to 8x8 primitive cells, consisting of 48 to 192 atoms. And the good thing in also the transition material is that you have only one more layer of metal, which means this is maybe computationally less costly than the mixing. And here they use Siesta basically, but contribution of my student Watha, she used VAS, and we focused on the hard metallicity to sharpen more the paper. So we did that. The second paper, it's about transition metal dihydrogenide, but it is due to the doped with transition metal doping of MOX2 to induce half metallicity, and we use it for and its relevance for gas sensing application. That's what and Wiping Fang from NUS, National University of Singapore, and myself. So this is already published this year, 2021. It's there in the paper done. So the first paper of defects. By the way, I'm presenting it because of the people from India, but I don't advise that we explore any defects in the future, because really it's not strategic way to do the half metallicity or anything else. So there are better always functionalization with the dopants are more attractive and more under control experimentally. So I think the defect is beyond control, and even the defect that we need to achieve the half metallicity are too dense, so experimentally not existing. So physically not really practical. But I'm presenting this because more of fundamental science, because it's really a nice citation or something, and it's under review anyway. So here with this supercell, for example, here 5x5, and I told you this, the people in India there, they use 4x4 up to 8x8, but here we show only 5x5, and they create vacancy here of molybdenum, and they create also vacancy of sulfur and disulfur, which means both sulfurs, and they relax the system, of course, and they look to the electronic and magnetic properties. So Monolayer, as I said before, there is the state splitting into 3 groups, but the lower group, which is singlet, consisting the valence band, and the doublet consisting the conduction band edge. And here we show the spin polarized band structure and density of state, total density of states. But it shows the total density of state space spin up, spin down. It shows symmetry, same symmetric. So basically there is no magnetism. Magnetization is 0. So it's paramagnetic. Okay. The monolayer in its pristine structure, it is paramagnetic. Okay. So if you create vacancies, here vacancy of molybdenum, second column is vacancy of selenium, and third row of vacancy of selenium, this selenium. Okay. So the all vacancies, also MOS2. MOS2 vacancies, all vacancies are paramagnetic. Only one case of molybdenum Se2, and with vacancy of molybdenum there is magnetism, because spin up, spin down in the density of states. I'm showing here on both bands and density of states. Total density is spin up, spin down, spin polarized, and moreover maybe in the column, left column that I'm pointing here. All of this, they are shown the results for 4x4, 5x5, 6x6, and we have 7x7, the same thing, but we put 8x8 to reduce a little bit the size of the view graph. So here we show the bands left for the density of states. The left ones are spin down, the right one is spin up, and we project them on the bands. Or the bands are projected on density of state, that's fine, but we just equivalency. So you can see here that the top one is the black ones are indicating spin down, and the orange ones are indicating the spin up. And also for the density of states, the red color is indicating the contribution from the neighboring sites to the vacancy. Okay, so these are the color code. So, but be careful, Narendra Kumar did a mistake here, because the orange ones should stand for the spin down, and the black bands should stand for spin up. But only one panel, there is a mistake. It converted. If you go to lower panels, all oranges are, all orange colors stands for the spin down, spin down, spin down. And the black color stands for spin up, spin up. Only this panel is, there is a mistake. The referee is also pointed the mistake to correct it. So I asked him to correct this mistake. Now it's maybe my opportunity to show it to him, maybe because he went to India when I started working on the revision. Anyway, so that's the thing, but you can see here there is magnetism because the spin up, spin down density of states are different, and moreover, there is distinction, and there is also, you can see at the sample 4x4, 5x5, it's half metallicity, because Fermi level, which is our reference 0 there, it meets with the spin up density of states. So there is spin up are metallic, while spin down are semiconducting. So spin up are metallic, but later on in the 6x6 there is loss of metallicity because the states become not anymore broad, but it becomes tiny, so it's localized. So there is, if you calculate DC conductivity, we expect that this state is very localized, not conducting anymore. So we don't have metallicity. So there is a big loss of half metallicity after the size 5x5. So more another remark maybe before I move, there is broadening when there is 4x4, the density of states at Fermi level for the metallic spin, it's the broad, whereas if you move it starts to get thinning. And don't forget that the scale of the energy is the same everywhere in the panels. So there is thinning of the density at Fermi level, which means the Fermi ferromagnetic interaction is getting weaker. Anyway, so we studied all this. Maybe I should move straight forward. But maybe the Indian group, they did study from 4x4 to 8x8, and they realized that the magnetization is always constant for all samples, which means the magnetization in the different sizes from 4x4, 5x5, 6x6, 7x7, 8x8, or the magnetization remains the same, but for Bohr magneton. So basically we have the half metallicity only in two cases, which are the samples of MOSE2 monolayer In case of 4x4, you can see here the black squares are due to the spin up, whereas the green full squares are due to spin down. Spin down semiconducting, spin up are conducting, and in the case of 4x4 and 5x5. So we investigated why there is half metallicity in this case. We have plotted the homo states using VASP. This is contribution by Watha. So we could see that 4x4 and 5x5 there is destruction in the spin down. So we plotted homo because it's semiconductor, and in the upper spin up is conducting. So we can see here they are delocalized, but the state starts shrinking by the increasing of the size of this sample, and we interpreted that by due to the ferromagnetic interaction with the images of the vacancy. Each vacancy, as you can see, we have periodic boundary conditions, so it has six neighboring vacancies because of triangular lattice. And there is disappearance of metallicity after 5x5. Okay, we also did the ODOS study by Watha in VASP. So we showed also the contribution is due to the mixing in case of especially spin up. You can see in spin up states there is mixing between molybdenum and selenium atoms. So therefore there is mixing. Moreover, there is also mixing between the in the ODOS. There is mixing between states which are z square and x square, y plus y square, xy. So the band edges, they mix up due to the ferromagnetic interaction. So that's the conclusion probably. Then I should move on because I described everything basically. Also the critical length for the existence of ferromagnetic interaction, it's also shown to be about 14 angstrom. Moreover, we tested also the sample, which is instead we took the 4x4 and we replicate in a sample of 8x8. So it contains 8 vacancies of molybdenum, and we studied the band structure and total density, the total energy, magnetization. It's about 16, which is about 4 times the magnetization of the sample of 4x4. Therefore, we are proving that there is ferromagnetic interaction where all the magnetic moments add up to 4 times. And we show here also again the spin up, spin down of the 4x4, which is we said that the spin up is metallic and spin down is semiconducting. So we try to show that the ferromagnetic state is consisting of the ground state of the system. And we tested antiferromagnetic state to be metallic completely. It's not half metallic, and it's not with total energy as low as the ferromagnetic state. Anyway, now I said probably in the beginning, I'm not going to finish describing everything, but now I will move to the paper of Watha on transition doping because it's more promising. Better than because here we have also an inconvenient, like I said, the density of vacancies is experimentally proven to be 3.5, 10 to 13 centimeter minus 2, which is the maximum density that can be in the samples. Whereas ours needs more density because one vacancy per sample of 4x4, it requires high density. So we don't have it experimentally available. So what to do? It's better to explore doping. So we did the doping by transition metal. These are the transition metal atoms. We scanned the transition metal from scandium to zinc, and we have shown the existence of metallicity in 7 cases. MOS2, when the transition metal doping is appearing on the metal and on the chalcogenide. But in the case of metal doping, we obtain half metallicity. And we obtain also what do you call it, magnetism or ferromagnetism. So the 7 cases are obtained where half metallicity observed. Transition metal when it MOS2 when it is doped with manganese and iron and nickel, and MOSE2 when it is doped with vanadium, manganese and iron and cobalt. So we did also some scaling to predict the ferromagnetic interaction, how to what distance it can be carried out. We proved to be also about 20 angstrom in case of transition metal doping. So here we showed our results of density of states. So I trust me that we investigated the cases of half metallicity, and here we show summary of the potential of ferromagnetic interaction. And the potential is divided by we take the bandwidth divided by 12 because we have 6 neighbors, and as you know, for minus v till plus v, and times the number of neighbors for minus 6v till plus 6v. Therefore, the bandwidth should be about 12 times the v. So V is for bandwidth divided by 12. So that's we call the potential of ferromagnetic interaction. Here I plotted it versus 3 dopants in case of MOSE2, where we said it's manganese and iron and nickel. And this yields the half metallicity. And MOSE2 we have four dopants, vanadium, manganese, iron, cobalt. And we show the samples 4x4, 5x5, and 6x6. So the V is reducing, and we could from there probably 7x7, we don't find any interaction. So we could estimate the scale of the ferromagnetic interaction. Anyway, we also tested to show the referees. Probably we did it before referees because our first submission it's under review. We submitted this one, I think, to the materials. So we tested the ferromagnetic state and anti-ferromagnetic state, and we have shown that the total energy is ferromagnetic. And this is sample of 8x8. This is our first sample that we want beyond 6x6 with WAPHA. So to test the 4x4 sample, like we did also in the case of defect or vacancy. So now thereafter we explored the half metallicity in gas sensing. So we did the absorption. We tested the absorption of oxygen, NO, NO2, CO, and H2, and H2S, and H3. And we tested the relaxation, atomic relaxation. We observed all of them. They are physiosorptions, all of them. As you can see this in the atomic structures, and we tested the bands and density of states, and we saw that there is only one case which is hydrogen, where the band structure remains basically robust, half metallic. Half metallic, as you can see here, spin up is conducting and spin down is semiconducting. So therefore, the absorption of hydrogen didn't change the half metallicity state, whereas the other all the other molecules, they are physiosorptions, but the von der Waals interactions affected the states at Fermi level and changes the state of half metallicity, and the half metallicity is lost. So we expect that the conductivity should be drastically changed, and so it will have a good effect on the gas sensing, where we in gas sensing, as you know, we care about the IV curves. How they rectified the IV curve are. So the conclusion of this second part that I ran very fast is that you have here we plotted the absorption energy absolute value and the absolute value of also charge exchange and absolute value of relative change of magnetization. So we can see here on all the steady 7 molecules in the gas sensing, in the absorption study that we did. So we can see here that there is kind of tendency towards selectivity toward an O2, because the huge change is attributed to those molecules to the sample. So on 3 aspects, on the absorption aspect, energy, absorption energy, and the change of magnetization relative 1, it's huge, almost 100%. And delta Q, the charge exchange. So our expectation is an O2 should be selected, or the selectivity goes toward the selectivity to an O2. If you use MOSE2 docked with MN. So we are not exploring different systems, only one case. We want to show one example of their relevance to gas sensing. So now, basically, I also described all this throughout my description. So I'm now, Kumar, now time is up. Should I move to the hydrogen storage, because very important? But the time is I'm running out. Exactly, I finished my view graphs of the first part. Second part, it will be just one paper to present. So far I presented 3 papers. So if you allow me to go continue, or maybe just we stop here and we leave it to another opportunity. either today, tomorrow, whenever you want to schedule a meet for another talk about gas and about maybe I can make collection of other topics, which are hydrogen storage and biomarkers, also, which is very important for biosensors, and batteries, and maybe gas sensing. I already explored the side of heart metallicity, but we would show that we don't rely only on heart metallicity. We rely on polarization, and when we adopt the transition-emitted chalcogenide, only when we adopt especially the chalcogenide side, so that we create a dipole. That dipole is very important to interact with molecules. So the dipole, it's so strong dipole to induce electric dipole moments into the molecule and enhance the van der Waals interaction. Enhancement of van der Waals interaction affect the Fermi states, which is very important. So it will affect the conductivity. So this philosophy of the doping the chalcogenide site to create stronger dipole. Stronger dipole interacts with molecules, especially when we talk about VOC or cancer lung biomarkers. The molecule is so large, so it creates many places where there is electric dipole moments. So the enhancement of van der Waals interaction with VOCs will be stronger than with their air molecules which come with the exhaled breath. So there will be stronger interaction. So stronger interaction affects Fermi level states. Affecting Fermi level states affect the conductivity. So very, very beautiful things that I will present thereafter. But either I stop here, like if you don't by time limitation, and they leave the other VOC interactions as well as hydrogens. Especially what gives us big hope is the interaction with hydrogen. So the doping of the chalcogenide site by a transition metal, it induces dipole moment into the hydrogen. And there will be strong interaction. So we stored about 76 molecules in a sample of 4x4 of transition metal chalcogenide. The uptake was raised when we docked only two sites. When you dock one site, you have about, I think, 30, 32 or something. When we docked the two sites, there is increase to 75 molecules were attracted to the sample. So they were maintained with energy absorption between 0.2 to 0.6, which is the range recommended by the International Atomic Agency for energy storage. So what do you call it? So the hydrogen was stored. Thereafter, based on our success on hydrogen storage, we moved to VOC and other applications. So magnetism. If you dock the chalcogenide site, you obtain dipole. The only one site, the MOS2, you dock only the upper layer or the lower. So the only one site, and you leave the opportunity to enhance the dipole, electric dipole moments. Thank you very much. So I have more work, maybe about less than this amount of time. But I leave it for you. If you want me to present it, I present it. I have the PowerPoint presentation. So a lot of effort. I thank maybe I have the view graph in the second part. I would like to thank my students Wadha Falasi. She did most of the work. Narendra Kumar, he did some contribution with the Indian group on defects, and yourself, Arun, and the Indian group. Maybe I should I stop sharing and share the view graph only to acknowledge the people. So maybe I go to, sorry, just for acknowledgement, and I stop. I go to acknowledgement. So this is the part, but I hydrogen start. The view graph of acknowledgement. The view graph of acknowledgement is that the financial support of both research office and College of Graduate Studies that are supporting Kumar at your university. And the grants for this grants, I have to be grants. Always I have to receive grants happening. One is support for PhD, one is support postdoc, and having postdoc data. My collaborators at US, Professor Yan Ping Funk, and of course they give us access to the HPC lab, which we are enjoying to have fast results and huge computers. My PhD students, Wadhal Palasi and Narendra Kumar. My collaborators in India, Anji Devi and Diman, Arun Kumar, PK Ahlawalia, and Singh. So these are the people that I know in this work. So meanwhile, for future work, as I said, I didn't complete even the research which I'm reading now. I told you about 3 papers or something or the other. Maybe I present at least 2 papers. What do you call it? Hydrogen storage and biomarkers, cancer biomarkers. But I leave it for you. If you are interested, I can do that. Also, I have batteries and gas sensing. All these are done by Al-Falasi Wadha. So thank you very much. But future work, you can see that I am writing that for transition methods can be used also for detection of VOC, non-cancers. But the results that are ready now are on mixing by Wadha. So the results mixing are ready, but for the transition methods, even Wadha, she did testing. She is very happy with them, better than even mixing. And transition methods are also the same thing. When you dock the X site or Shackleton site for battery applications because of induction strong of dipoles, so they might interact also with the ions of the battery more, and we enhance maybe uptake capacity, or what you call reversible